Today we're talking about normal distributions. So these are a special class or type of distribution that differs from the ones that we've talked about so far in a couple ways. The first one is that this is a model. Rather than taking some finite collection of data points, like let's say we asked 50 Stat 11 students how tall they were, what this is talking about is an idealized situation, saying things like real life distributions are going to roughly follow this idea. The other main difference is that this distribution is continuous. So unlike the other distributions we've talked about, which can be seen in nice rectangular histograms, this one is smooth. We're first going to talk about these distinctions, and then we'll get into how we can actually apply this distribution to some real-world ideas. Normal distributions are characterized by this bell curve shape, and this general shape of the distribution shows up a lot in the real world. Things like probability, things like measurements such as height and birth weight and shoe size and these types of things often generally follow this bell curve. That said, no distribution ever is going to be exactly the bell curve. Real-world data is inherently messy, especially when dealing with relatively small sample sizes. One or two slight deviations make our data look, noticeably different. But often when we increase the sample size, we can see that our picture, our histograms, look closer and closer like this bell curve. So for large N, for large sample sizes, this normal distribution actually does a very good job of explaining roughly what's happening. But I want to focus on that part. It's always going to be roughly what's happening. This is a model. This is an idealized situation, which is never going to be exactly right. But for most intents and purposes, it's usually going to be good enough. A key feature of this normal distribution is that it's characterized entirely by two numbers. Once you specify what the mean of the distribution is and what the standard deviation is, then the rest of the picture falls into place. So as we have it now, this is the normal distribution with a mean of 0 and a standard deviation of 1. We can adjust that mean, and we'll see that the entire picture slides to the right and left, but maintains that bell curve shape. Similarly, we could change what the standard deviation is. So if we were to decrease the standard deviation, we would see that the entire distribution gets more narrow, but still, broad strokes, it's still this bell curve shape. And it's going to maintain certain properties that we'll talk about moving forward. We can also increase the standard deviation, and it's going to widen out this bell curve. We also said that this is a continuous distribution. In contrast to the discrete distributions we've talked about so far that have histograms, this has this smooth curve. One adjustment that we have to make when talking about or asking questions about these continuous distributions is that we can't really ask how many people have a specific value. We instead have to ask about ranges. Okay, let's take an example here. So here we have a normal distribution representing heights of, I believe, women in North America, which has a mean of 65 inches and a standard deviation of 3.5 inches. Okay, so if I were to ask somebody how tall they were, and they responded, oh, I'm 5'10", in other words, 70 inches, they don't mean that they are 70.000000000 inches tall. What they really mean is that they're roughly 70 inches tall. Typically, if you say that you're 5'10", what you really mean is that you're closer to 5'10" than you are to 5'9" or to 5'11". So really what you're saying is, rather than being exactly at 70 inches, you're somewhere in this shaded region. So if we wanted to know how many people are 5'10", what we're after is what is the percentage or what is the number of people in the distribution who fall in this particular shaded range. And when we're working with normal distributions, the questions are always going to be phrased like that. How many people fall in a certain range, rather than how many have a specific exact value. Because this is a continuous distribution, it doesn't really make sense to talk about a single exact value on this. We're always talking about a range. All right, here's a question. What percentage of people are between 58 and 72 inches tall? Assuming that this distribution even follows a normal distribution, which we just finished saying isn't something that happens in the real world. So this question is much more about this hypothetical model than some real world values. So in other words, what proportion of this distribution lies in this range? And before we jump into how to answer this question, I want to point out that this is actually a really important idea. We're going to be using this notion of a percentage of a normal distribution in a certain range to answer questions involving inference later on, and this is going to be used in a bunch of different ways that we'll get to in the future. But for now, we're just asking what percentage of people's heights fall in this range. Since this normal distribution curve is measuring proportions, the thing that we're after is actually usually the area under this curve. The proportion of the whole, or the percentage of the distribution that falls in a certain range, is the same thing as the area of that range. So if you've taken calculus, you may be tempted to say, oh, area under a curve, I just want to integrate this. Well, the problem there, and the reason we have to jump through sort of an extra hoop, is that the function that determines this normal distribution is kind of really messy. And even if we were to simplify it some, it still is of a form that you may recognize as one of those functions that doesn't have an antiderivative. So taking an integral here, while computers can solve it numerically for us, is not something that we want to actually do. Instead, we're going to rely on some estimation tools, or just by asking a computer to say, what is the area of this region? What is the percentage of the population that lies in this region? Okay, in order to answer this question, we're going to translate the endpoints of the region that we're talking about into z-scores. We want to be talking about how many standard deviations away from the mean a certain value is, rather than its absolute measurements. So since our mean is 65 inches and our standard deviation is 3.5 inches, we can see that this 58-inch cutoff is a total, well, it's 7 inches below the mean. Well, 7 inches is 2 standard deviations. Therefore, 58 has a z-score of -2. So the range that we're looking for is 2 standard deviations below the mean through 2 standard deviations above the mean. By translating into this z-score language, we can take units completely out of the picture. Rather than having to specify which of the many normal distributions we're talking about, what we're really focused on is this proportionality of this distribution. So the question of what percentage of the distribution lies between z-scores -2 and +2 is just a fundamental question about the form of a normal distribution. A useful tool for answering that type of question is the 68, 95, 99.7 rule, which talks about exactly this. What percentage of the distribution is within 1, 2, or 3 standard deviations of the mean? So as it turns out, if what we're interested in is how many people are between 58 and 72 inches tall, well, that's just going to be 95% of the population. Now, these numbers were chosen because they were relatively easy z-scores to calculate. It's a nice whole number. We also want to be able to do this type of analysis when our z-score isn't one of these cutoffs. That said, for rough estimations, this rule is actually really useful and can get you pretty close when estimating what percentage of a population is in a certain range. Let's ask another question. What if instead I want to know what percentage of people have heights less than 63.25? Now, you might notice that 63.25 is half of a standard deviation below the mean. So we can recast this question in terms of a generic normal distribution. We don't need the extra information about heights and such. Instead, it's just a fundamental question about normal distributions, and that is, what is the percentage of the distribution that lies in the region from way off to the left up to z equals negative 0.5? And since this is a fundamental question about something that's used fairly often, there is an R function that tells us that. So if we go to R, we can use the p-norm function, which has several options as to some extra information you can provide it, but at its basic level, you can just feed in a number like negative 0.5, and it will spit out that answer that we're looking for, the area under the curve from negative infinity up to negative 0.5, aka the percentage of the normal distribution that's less than this cutoff, z equals negative 0.5. Just to double check this p-norm function, let's try a couple other values. As in, let's try p-norm of 0. So go ahead and pause this video for a second and think to yourself what you expect p-norm of 0 to be equal to. Okay, so p-norm of 0 is asking what is the area under the curve from way off to the left up until right in the middle. If the whole thing is 100%, then half of it should be 50%. So p-norm of 0 equals 0.5. Here we're making use of the fact that this distribution is symmetric. Okay, here's a slightly trickier one. What about p-norm of negative 1? Here we could actually use the 68, 95, 99.7 rule. The 68 is telling us that within one standard deviation of the mean lies 68% of the distribution. That means that the remaining 32% is outside of that middle region. And exactly half of that is on the left side. In other words, this should be half of 32, or roughly 16%. To sum up, normal distributions are these infinitely wide bell curves whose shapes are dictated by the mean and the standard deviation. If we have some question like what percentage of a distribution lies in a certain range, we can convert those endpoints into z-scores, and then the question becomes a fundamental question about the shape of normal distributions. These can be found using calculators or by using one of the rules that we know. These normal distributions are going to show up a lot moving forward, especially when we start talking about probability and inference.